Hello everyone, this is the second video lecture for chapter 20, module 4. In this video lecture I will be covering the remaining topics in the chapter, specifically Ampere's law and the force between two current carrying wires. Okay, so let me go over those. And by the way, Ampere's law is in section 20.10. Let me go there very quickly. We are in chapter 20. 20.10. There it is. Magnetic field calculation, and this is Ampere's law right here. Okay, so I'm going to go over that, and I'll give you some examples, and then we will have the next topic is the force between two current carrying wires, and then the remaining part of the video I will go back to the end of the chapter, and maybe I will do a couple or three problems from the homework as well. Okay, some have to do with Ampere's law and the others have to do with the previous topics that we have covered. So let me just review what we have covered last time. We basically covered two major formulas. Both of them have to do with calculating the magnetic force due to a charge or to a current carrying wire. So the first one, we said that the magnetic force F sub B is equal to QVB sine phi or theta. And this specifically, this formula specifically talks about if you have a charge, say positive, and it's moving with a certain velocity, and it is in the midst of an external magnetic field on it. Okay, as a result of that, there will be a force on the charge, and that force, if you use the right-hand rule, it will be pointing in the upward direction, F sub B, let's call it, and that F sub B is equal to the magnitude of the charge, Q, okay, multiplied by the velocity of the charge, times the intensity of the magnetic field in Tesla, times the angle, if there is an angle. Most of the time that we deal with, if the angle is 90 degrees, so sine 90 is 1. So basically the problem or the equation reduces to QVB. If there is an angle, you want to put that angle sine whatever that angle is. So that's the first formula that we dealt with. The second one, if I have a current carrying wire, basically a wire that has a current inside of it, and this wire, let's call it a wire segment of length L, for example, and then there is a current going through it like that, and then there is a magnetic field on it. Let's say it's into the page like this. And remember, this is an external magnetic field like that. And there will be a force on it that will be pointing in the upward direction. Basically, it's going to tend to literally lift the wire up. You know, say if it's sitting on the table, it's going to lift it up. That force F sub B, this F sub B is going to be equal to ILB sine the angle, if this angle is there. If this angle is between the magnetic field and the length of the current. Okay, those are the two formulas that we have dealt with. Again, I'm gonna do maybe a couple of problems from the homework where you have to use those equations to solve it. All right, now we come to the next topic, and that is Ampere's law. Ampere's law says the following: any current carrying wire, any wire that has a current in it, okay, there is an associated magnetic field to it. Okay, so for example, you know, you're using your computer right now, and behind your computer there is, they say, the power plug, and then you got the wire there. That wire, because there is electricity going through it, there is an associated magnetic field in it, okay? And it basically looks something like that. Here is the wire. Let me put it vertically. here is the wire right here, and let's assume this is the wire segment, that is, okay? And let's assume here is the current going in this direction. By using the right-hand rule, there is a magnetic field that is going around it, literally going circulating around it. This magnetic field B is that is associated with that wire is equal to B equals to, as shown in the formula in the book. Let me just show it to you right here, mu naught I over 2 pi r. I'm going to explain what that means in a sec. So it's equal to mu naught I over 2 pi r. What does that mean? First of all, mu naught here is a constant, okay? And it is called the permeability of free space. It's not really terribly important that you have to know what it is. You can look it up if you want to. But it's basically a constant that is equal to 4 pi times 10 to the negative 7 Tesla meter per ampere per amp, okay? Tesla meter per amp. What's important is the constant itself. This constant basically was created because we want to emphasize that we are using Tesla, and that's an SI unit. So that constant was created because of that. But anyway, that's basically what it is, just a constant. So it's nothing more a constant. Of course, I here is the current, and it's measured in amps. And then you have the distance R. Okay? What that means is the following. If I have a wire, okay, and this wire, let me go back to this same picture that I had drawn. Let me draw it again. So I have this wire like that. Here is the current. Just because it has a current, there is an associated magnetic field that is generated because of that current, okay? Let's assume that I'm interested in finding the intensity of this magnetic field right at this point P, at the distance R away from it, okay? So I want to know what is P here, okay? First thing I need to do is what is the direction of this magnetic field? And second, what is the magnitude? To find the magnitude of it, it's simply that formula that I just showed you right here, okay? In other words, if I say that, let's say that this wire has a current of 5 amps, and I want to know what is the intensity of the magnetic field at 10 centimeters, okay? I simply say, well, B equals to mu naught I over 2 pi r. I can just plug in all those values. So mu naught, as you can see here, it's 4 pi times 10 to the negative 7 times the current, which is 5 given to us, divided by 2 pi times r, which is 10 centimeters, which makes it 0.1 meter, correct? Of course, the pi's will cancel out. As you can see, the 4 and 2, you'll get 2 here. So basically, and then of course, this 2 right here, and this 5 becomes a 10. 10 times 10 to the negative 7, that will give me 10 to the negative 6, correct? And then this 1.1 is basically 10 to the negative 1. I'm trying to do it without a calculator. So that's 10 to the negative 6 times 10 to the positive 1. So that's just 10 to the negative 5 Tesla. There we go. So I have calculated the magnitude of that, the magnitude of the magnetic field that is associated with this wire at a distance 10 centimeters away. You got it? That's basically what it is. So that's what Ampere's law allows you to do. Now, the second part is, what is the direction of it? So what is the direction of that magnetic field? Is it in or out? So this is magnitude. What about the direction? The direction requires you to use the right-hand rule, but it's in a different way. So I have prepared a video for you. Again, you can go back to YouTube and then just type in Ampere's law right-hand rule, and you'll come up with tons of videos. Watch them all until you get it through your head. I mean, one of them is gonna, have you understand what that is. So anyway, I prepared one of them. Here it is. This one called Ampere's law, and the channel is Mr. Way this class. I don't know. Here it is. Okay, you can take it out. And anyway, he talks about Ampere's law, but it's starting somewhere here. Let me just, there we go. Maybe right here.
Ampere's law for the closed right-hand rule. I'm going to use my right hand. I'm going to close it and stick my thumb out like I'm hitching a ride. So here it is, my thumb. It's pointing right towards me because it's a dot coming out of the screen. And on the screen itself...
Okay, imagine that this dot is actually the current. So imagine the current, the wire here. See this wire going up like that? Imagine this one up, and it's basically on the screen going toward your face. You got that? So this is going toward your face. So your thumb will be pointing towards in the direction of the current this way. Got it?
My fist is sitting there on the screen and making a circle.
Do you see? Oh, I'm sorry. Do you see the curl of his fingers? That's basically the direction of the magnetic field. So the thumb is pointing towards in the direction of the current, and the curl of his finger, do you see the circle right there, those arrows? It's basically the direction of the magnetic field. Got it?
So that's the direction my fingers are rotating. That's the B field. And the question is, what's going on above the flow? So in this little box, that's above the flow. And above the flow, the B field is tangent to the circle, pointing from right to left. So that's the direction of the magnetic field above the flow. That's the answer. But when you're looking at questions, you can also talk about other parts of this, as well as this point above.
I'm going to stop the video here, but basically you can watch the whole thing if you want to. Another video that I have is this gentleman right here. He has a channel called Bright Storm. He's really good. Very, very good teacher. He explains things. A little crazy, but he is, it seems like his target are high school students who are taking physics. But he explains things very, very well, and I discovered his video. That's him.
Lecture, and he noticed that
this lecture is only 7 minutes, but it talks about the Ampere's law.
A magnetic field was generated that moved around a compass needle when he ran a big current through a wire.
He's telling some story. Anyway, if I go further there. Sorry, I didn't prepare when. At some point, he will show with his hand how to calculate the magnetic field. It's not here. Anyway, you can look him up. Again, I recommend him, but that's just my opinion. The title, Ampere's Law, and it is Bright Storm. Okay? He has a bunch of videos on many things and many topics in physics. Anyway, I'm going to leave it here. Hopefully, with those videos and others, you will come to understanding how to calculate how to find the direction of the magnetic field using the right-hand rule. Okay, for Ampere's law. Remember, there are two right-hand rules. One for finding the magnetic force, which we covered in previous video lecture, and then you have how to use the right-hand rule to calculating the direction of the magnetic field. Okay, so please take that seriously, because just about almost 70% of the problem that we deal with requires you that you have to use the right-hand rule to do that. Okay. All right. All right. Back to class. So basically, if I want to do the right-hand rule for this one here, so it's basically, if I would grab imagine that I would grab this wire. I can grab it with my hand in such a way that my thumb is pointing toward in the direction of the current, so the curls of my finger is going to be like that. Like that, see what I'm saying? So in this case, if I am looking at the magnetic field here, it's going to be into the page. Where if I'm looking at it in this side of the wire, it's going to be out of the page, because it is out in. See that? Out in. See what I'm saying? The curl of my fingers around it. The best way to do it is hold the pencil on your hand, where the pointed side is in the direction of the current, and then grab it with your hand and see the curl of your finger, and you will see what I'm talking about. I hope. Okay. So basically, there it is. So the direction here, as far as point P is concerned, the direction of the magnetic field is into the page. If point P was in the other side, right here, for example, let's say another point, let's call it point, say Q, or Q is not a good idea. let's say a point n. Okay, so in this case it is out of the page, right? This is out of the page. So this is into the page, and this is out of the page. See what I'm saying? It depends the way you are, you know what I mean? Okay, so anyway, so with this problem, so the direction is into the page, or into the screen, or whatever you want to call it. Okay. Now also we have a sign convention. The sign convention is this: if you have, if the magnetic field is out of the page, it's positive, and if it is into the page, it's negative. Okay, this is the convention that we're going to adopt. You see what I'm saying? Convention. Did I spell it wrong? Let me. Okay. The second topic, I'm going to do some problems, I promise, but I want to cover both topics quickly, and then we'll do some problem. The second topic that I want to cover is the force between magnetic force, that is, right? We're talking all about magnetism. So this is when we say force here, we mean magnetic force. So magnetic force between two current carrying wires. What that means is the following. Imagine I have two wires and they are parallel to each other. Okay, here's the first one, and here's the second one. I'm going to put them horizontally like that. They can be vertical or whatever. And for simplicity, we're going to take them to be parallel. We will always take it to be parallel in this course. And let's assume that we're going to call this wire number 1. Sorry, let's make it wire number 2. I'm kind of following my notes. And this is the wire number 1 right here. So this one coming out of it, or going through it rather, current I2, and this one current I1. Okay? Now I want to use Ampere's law. Oh, hold on. So again, let's assume both wires have the same length. So let's call the length L. And both of them have L's, okay? And they're both separated by a distance, let's say D, small letter D. Okay, so far? Okay. So that's basically the picture that we have. Now, according to Ampere's law, for any current carrying wire, there is an associated magnetic field, right? So if I'm going to use the right hand rule, to find the direction of the magnetic field B1 due to I1, okay? So if my thumb is pointing in this direction, the curl of my fingers are going to be in that direction. So basically, it's going to be, on this side, it's going to be out of the page, and this one is into the page. The curl of my fingers are going to go out of the page here, into the page here, because I'm grabbing it. Okay, and again, grab your pencil horizontally, okay, such that where the direction of the pencil is in the direction of the current this way, and you'll find that the curl of your fingers are pointing, or the tips of your fingers are right here, or rather they are pointing out and into underneath the pencil and out to and above the pencil. I hope you see that. Okay, so in this, above the pencil, above the wire, you have the magnetic field pointing out of the page. So of course it's going to be also about pointing out of the page here. So it's going to be out of the page everywhere, if you know what I mean. Like that, everywhere. Above it, okay. Below it, it's X into the page, but we're not concerned about that. Okay. So in other words, this I2, as far as I2 is concerned, is going to feel, quote unquote, it's going to feel that there is a magnetic field, an external magnetic field, B1. Because remember, this is B1. This magnetic field here is B1 due to I1. Okay, so I2 is going to feel an external magnetic field, B1. So here we have, in this case, that it will feel a force. That force is going to be pointing in the downward direction. I'm going to call it magnetic force, F2. And this F2, again, this is using what we covered in the last lecture, is going to be equal to I2 B1 L. You can pause this video and think about how I came up with it. The same thing, of course, is happening with I1. So you have I2 coming, I2, you have the direction of the current I2 going this way. And of course, I2 also is generating a magnetic field, B2, and that B2 is going to be felt, if you will, by I1. Okay, and eventually what you will see is that there will be a force F1 here, magnetic force F1 is equal to I1 B2 L. Okay, now one more thing. If going back to the current I1, if I use Ampere's law because I want to find the magnitude of B1, well, Ampere's law says what? Mu naught I1 over 2 pi. Of course, we're looking at it here, which is at the distance d. So 2 pi d. So now if I take this one and plug it right in here, so F2 is going to be equal to I2 times mu1 I1 over 2 pi d L. And if I write it in a better way, I can write it this way. The force is going to be equal, F2 equal to mu naught over 2 pi I1 times I2 over the distance d times L. That's the formula. I want to write it in a different, one more version to it, where I take the L here and put it underneath that, okay? So it can be also written as F2 over L mu naught over 2 pi I1 I2 over D. So basically, I have just derived what is the force between two wires. If you don't understand it terribly, that's okay. I'm not going to be asking you how to derive it. But basically, the important thing is you need to learn how to use this formula, okay? And that's the easy part. So what it says is the following. If I have two wires, let me put them vertically this time. Here's one, make them just a little bit shorter, stubby. Here's another one here, okay? And I have current I1 and this is current I2. And if both are going in the same direction, there will be an attractive force between them, okay? There'll be an attractive force. So the same direction implies attractive force, attractive magnetic force. Okay, and if they are going in the opposite direction, here's the wire. Let's say this one is going this way, I2. Again, the currents are not necessarily equal. That's why I call them I1 and I2. And then let's say this one is going this way, I1. There will be a repulsive or a repulsion force between them. Both are equal. The F, this F, and this F are equal. And so in here, if the opposite directions, I should say, directions, so there will be a repulsion or repulsive force between them, okay? And both of these forces basically given by this formula right here, okay? So I'm going to write it generally speaking. This force is equal to F equal, without the F2 or F1, is mu naught over 2 pi, okay, that's just a constant, multiplied by the product of the two wires divided by the separation distance between them, okay, times the length of each wire, assuming both wires have the same length, okay? We're not going to deal with wires if they're not the same length. That requires a little bit more complicated, and this is above the scope of our course. So if we assume that they are separated by a distance d, and each wire has a length segment, line segment, length of L, okay? So we get this formula right here. But that's all you need to know about it, okay? And I'll show you some example. I'll give you one example from my notes. So those are the two remaining formulas for this chapter. Now we're dealing with 4 formulas. But here's an example. And I think it's example, oh, I have it in the book, 20.7. Let's go to it. 20.7. Let me find it in my hard copy. It's kind of easier to find. Oh, okay. It's section 20.8 says force between parallel conductors. That's basically what we have just covered. But anyway, it's on page 654. 654. There it is right here. Magnify it. Okay, it says, there we go, start from here. It says 2 straight parallel superconducting cables 4.5 millimeter apart. There they are. Here's one cable right here. Here's the other one. They're separated by, they both have the same length, okay? And then they're separated by 4.5 millimeter, okay? Apart between centers, carry equal currents, 15,000 amps. So we got 15,000, 15,000, but notice that this one is going to the left, this one is going to the right, okay? In opposite direction. What does that mean? Opposite will be, they will repel each other, okay? But again, the formula is the same. And now he says, find the magnitude and direction of the force per unit length. What does that mean? He really wants this one. Let me go back to what I told you. Remember we said that F equals that, or F over L. This one right here is called force per unit length. I'm sorry, I forgot to mention that. Okay, the reason it's written like that, if the problem asks you force per unit length, you basically find F over L. Okay, if it says find the force, you just want to get this one, but provided that you know what the length of the wire is. But force per unit length will give you that. Got it? Okay. So he says here, find the magnitude and direction of the force per unit length exerted by one conductor on the other. Should we be concerned about the mechanical strength of these wires? Okay. So let's see how we do that. So first of all, I want to write down what's given to us. .7. He said the length of each wire, I forgot to see what's in it, 1 meter, okay? Even though it's not important, because he said per unit length. And then the separation distance, I'm calling it D, is 4.5 millimeter. And the current, both of them, I1 and I2, is 15,000. Okay? And here's a picture. Oop. Here's the first wire. Here's the second one. Just like that. So one going this way and the other one going this way. Both have I1 and I2. They both have the same. And then the distance, separation distance between them is 4.5 millimeter. 4.5 millimeter, yes. Okay. All right. So how do we do it? The force per unit length, so just going to be F over L, which means the length is not important anymore, is equal to mu naught over 2 pi I1 times I2 over the distance between them, D. Okay? I believe your book uses R or D. Yeah, your book uses R for the distance between them, right there. See that? I'm going to stick with D. It doesn't matter, really. So we just plug it in. So we have here, mu naught is 4 pi times 10 to the negative 7 divided by 2 pi. And then I1, I2 basically both have the same, so just 15,000 squared, is that right? Divided by the distance between them is 4.5 times 10 to the negative 3. And then we just calculate that, you see what I'm saying? And of course, always what's cool about the mu naught and the 2 pi, you can see it all the time, they reduce to 2. So basically, you just get that 2. So 2 times 10 to the negative 7. And then you work it out, and then I'm just going to get the answer, cheat the answer from the book. It says 10 to the 4th. 10 to the 4th. And what's the unit on it? Since he said force per unit length, it's just going to be Newton per meter. Got it? Okay. All right, good. Okay, let's do some problems. I think this is it. That's all I wanted to talk about. My intention in this video lecture is to do some more problems. So let me start with, I had a piece of paper here prepared, right here. Okay, let me start with number 31. 31 has to do with stuff we covered in the previous one, and also I want to do number 6. That also has to do with the previous video lecture. All right, number 6 and 31. Let me start with 6. Both homework. We are in chapter 20. Just go back. Go backwards. Oh, I know the page number. I always forget that I have the page number. 663. Number 6 can be a little bit toughy for some of you. It's more of a math problem than anything else. Here it is right here. It says if the magnitude, let me just move it to the side. He says, let's put it in the center, sorry. Okay. He says if the magnitude of the magnetic force, okay, the value of the magnetic force on a proton is F. Okay, he didn't give you a number, he just says F. Is F when it is moving at 15 degrees with respect to the field. What's the magnitude of the force in terms of F when this charge is moving at 30 degrees with respect to the field? Okay? So, how do we do this problem? Okay. The difficulty of it really involves the math. It's not the physics. So he says, let's take some notes as we read it. He said the magnitude of the magnetic field, okay, so we have a proton, and then he says the force F when phi is equal to 15 degrees. Got it? That's what he says. He said the magnitude 15 with respect to the field. What's the magnitude of the force in terms of F when this charge, when the proton, is moving at 30 degrees with respect to the field? So when phi is 30 degrees, what is F here in terms of this F? See what I'm saying? So, all right, let me show you, how you let's start the problem. Okay, I know that obviously we're dealing with a proton, and they're dealing with a force and an angle, so obviously the equation that we're going to be using is the force due to a moving charge. Yes, the magnetic force that is due to the moving charge, and that magnetic force is equal to F equal to QVB sine phi. We're going to put that sine because the angle is there. Okay, and for our case, since it's a proton, the force that we're dealing with really is EVB sine phi. There we go. That's basically the equation that we're going to be dealing with. Now, how do we do it? Well, he says here theta changes. If it's 15, we get the value F. What if it's 30? What do we do? Now, one way to do it is that you can use the double angle formula, okay? Or there is a simpler way. I'm going to use both of them. How about that? Let me show you one way to do it. Remember, he didn't give us B or V, okay? But the good news is B and V are the same for both situations, for the 15 degrees and the 30 degrees. This is good news. Of course, we're dealing with the same proton, so also E is the same. So everything E, V, and B is the same regardless of the degree, the angle. The difference here is the F and the phi. You got that? So what I would do is this. If I take this sine phi and move it to the other side, okay, I'm making a trick here because I want to solve it. F over sine phi, and for our situation in terms of the 15 degrees, it's going to be F over sine 15. I can get that value of sine 15, but there we go. For the next, for the other one is, let me call it F2 over sine 30. Now remember, go back to this one. F over sine 15 is equal to what? Is EVB. Is that right? Remember, I took this sine and moved it to the other side, so what's left is EVB. Well, if I have the same formula, so in this case, F over sine 30 is also EVB. See that? So that's also equal to EVB. What does that mean? If both of them equal to EVB, that means this ratio and this ratio must be equal. You see that? You see the trick? So therefore, F2 over sine 30 is equal to F over sine 15. And all I need to do is to find F2. F2 is equal to, well, sine 30 is a half. So that's going to be sine 30 times F over sine 15. And I can just use my calculator. I don't need to do anything fancy here. So just, I know sine 30 is half, so that's 0.5 divided by sine 15. Answer 1.93. So F2 is 1.93F. That's the answer. That's it. Because he said, look, he said, what is the magnitude of the force in terms of F when this charge is 30 degrees? Well, it is, what's the magnitude? 1.93F. See what I'm saying? Here's another way of doing it. Start with the formula for the 15 degrees. So F is equal to EVB sine 15. Is that right? And leave it like that. Don't get the value yet. Got it? Okay. Now, sine 30, that's equal to sine 2 times 15. Make sense? Now, what does that mean? Well, remember the double angle formula in trigonometry? Sine 2 theta is equal to 2 sine theta cosine theta. That's the double angle formula. You can always look it up. Okay? So now, if I go back to F for the angle 30 degrees, that is, that's going to be FEVB sine 30. Well, that's EVB sine 2 times 15. I'm making a trick here. Now that's equal to EVB. Now use the double angle formula. It's going to be 2 sine 15 times cosine 15. Okay? So now what I want to do, this sine 15 with EVB, Well, what is that? That would be, let me go back. I'm sorry, I should have called it F2 here because it's different. So in this case, that's F times 2. What's left is 2 and cosine 15. 2 times cosine 15. Now I just need to calculate that with my calculator, and I bet you it's going to be 1.93. So let's do that. So I can have cosine 15, that's equal to 0.96, multiply that by 2, and that's equal to 1.93. So if I calculate that, it's going to be 1.93f. And there we go. See that? I think the first method is easier, but you know, whichever method you make you feel comfortable. There we go. Got it? Okay. Number 31. That's another homework problem. It's on page, when I find it, 665. Right here, but start with the bottom of the page. There it is right here. That's the picture that we're looking at. He says a long wire carrying 6 amp current reverses direction by means of 2 right-angle bends. See, the current is going this way initially from left to right, and then it goes through. This is the 2 right-angle bends like that. There is a magnetic field pointing out of the page. You see what I'm saying? The width or the diameter of the magnetic field is 75 centimeters. And then so it goes this way and then down and then this way. And the width of this rectangular wire is 45 centimeter. Got it so far? Okay. So he said a long wire carrying 6 amp current reverses direction by means of 2 right-angle bends. The part of the wire where the bend occurs is in the magnetic field of 0.666 Tesla. Okay? So the intensity of the magnetic field here is 0.666 Tesla, confined to the circular region of diameter 75 centimeter. Question: find the magnitude and direction of the net force on that magnetic field exerts on that magnetic. Let me repeat it again. I'm sorry. Find the magnitude and direction of the net force that the magnetic field exerts on this wire. Okay? All right. Let's see how we do this one. That's basically a force between 2 parallel conductors. Okay, number 31. Okay, so the picture looks something like that. I need to draw the picture. Always draw the picture. It really helps you solve it. Here it is. Here is the current going this way. And there is a region, a circular region like that of the magnetic field. And it is out to the page like that. Okay. And the magnetic field B is 0.666 Tesla. The diameter here is 0.75, or is it 75? 75 centimeters, sorry. And the width of the rectangular loop is 45 or 4.5, I don't know. 40, yeah, there we go. 45 centimeter. Okay, now, remember we talked about when we have wires. So here you have a current going this way, and then you have a current going this way in the opposite direction. What will happen when you have 2 wires that are identical like those, that have a current going in the opposite direction? Let me show you the picture. There it is. If they're going in the opposite direction, where are they? There it is. This one and this one, I1 and I2. So you get the forces in the opposite direction. See that? In other words, they will repel each other. You got it? So in this case here, those two forces are going to be repelling each other. However, we have here an external magnetic field. And remember from our previous video, we said that if you have a wire, let's say here's a wire. Let me just go back and review this very quickly. If I have a wire and I have a current going through it like that, and then let's say I have a magnetic field that is external to it. This is an external. This is not generated by the wire, by the current. Okay, so in this case, if you use the right-hand rule, that's going to be a force going in this direction. Is that right? Let me check. This way, and this, yeah, it should be downward this way. Okay, now if the wire is going in this direction, again, you want to use the right-hand rule, and the current is going this way, and it's the same thing in this direction, so that force is going to be upward this way. Okay, and what will happen, because they are opposites in direction, so they will, by symmetry, they'll equal and they will cancel each other out. So basically I have two forces here, one going this way and one going this way, and those two opposing forces are going to cancel each other out, and the net force is going to be really is on the current that is going in this direction right here. Okay, so in this case, if I use the right-hand rule, it's going to be equal to a force going this way. I'm going to call it F. Okay, let's say this segment, I mean, I can imagine probably some of you are confused why this will cancel. Well, let's see. You agree with me that this segment and this segment are identical? They're very symmetric. In other words, the force here and here would be exactly the same. You agree with me on that? I hope you do. Okay, so if I call this segment, let's say, let me call this point A, okay? I want to make sure everybody understands what I'm trying to say. So in this case, this force, I'm going to call it F sub A, and this force right here is F sub B, okay? So this force right here, F sub B, this one is F sub B, F sub A, and then this, I have this other force because of the segment, this wire segment, going to be this way. So now, he said the net force, the sum of the forces is equal to what? Well, it's going to be equal to minus FA plus FB, and those two, as you can see here, because they're both equal, but FA equals to FB in magnitude, so they're going to cancel out, okay? So the only remaining force here is going to be F sub C right here. See what I'm saying? This is in the Y direction. So in the X direction, it's just going to be minus F. I mean, we can ignore the minus, but anyway, that's just the direction, so the force is toward the left. So that's basically what it is. Now, what is that force is equal to? Well, it's equal to ILB. Is that right? I mean, sine theta, but theta is 90 degrees. And that's it. We're done. So in this case, I'm going to, we have minus the current. The current is 6 amp. He said the length of the wire is, what's the length of the wire? This segment right here is equal to 45 centimeter, right? So that's going to be 0.45 times how many Teslas? 0.666, and then we would calculate that, and it will get 1.8 Newton, okay? So that's basically what the force F is, okay? Now, let me go back to the question. Is he asking for that? He said, find the magnetic direction of the net force that the magnetic field exerts on it. It's right here. This minus sign, I'm not sure how your mastering is going to do it. Maybe to the left or minus, I don't know. But anyway, that's basically how you do it. Okay, I hope this is clear. If it's not clear, let me know. Okay, good. One more. Trying to find another. Oh yeah, I know which one. This is not homework, but it's in the end, from the end of the chapter, number 83. I like this problem, 83. Should have assigned it as homework. Let me show it to you here. 83, page 668. Right here, okay, 83 right there. I believe it's not homework. There it is. Okay, it says let me make it as big as possible. There we go. Right there. Look at the picture right here. It says a pair of long, rigid metal rods, there they are, this one here and the other one in yellow, each of length L, lie parallel to each other on a perfectly smooth table. Their ends are connected by identical, very light conducting springs of force constant K, the stiffness constant, and negligible stretched length. All right. If the current I runs through this circuit, there we go. See the current going this way and then through the wires and back here and then through the wires, through the springs, excuse me, and then so it's going around in a circle like that. All right. If the current I runs through this circuit, the springs will stretch. At what separation will the rod remain at rest? Assume that K is large enough so that the separation of the rod will be much less than L. Okay. So basically it will create a force because of Ampere's law. And let me make a drawing for you. What you have in here, try to move it to the side. No way around it. Oh well. Okay. Okay, so what you have in here is you have those two rods. There they are. Here's another one. They're both identical. And then you got those springs right here. Like that. Okay. And of stiffness constant K, length L, and stiffness constant K as well here. So we have a current going this way, and then a current going this way. Okay, so it's going basically the same current going around, going around like this in a circle. All right. He wants to know the force between them. Now, would the force here be attractive or repulsive? What do you think? Well, as you can see, Ampere's law, right? There's no external magnetic field, so this the magnetic field there is generated by the wires. So we said that if I have two oppositely charged, opposite current going in the opposite direction, I'm trying to find it out. There we go. If going in the opposite direction, they will be opposing each other. See what I'm saying? Okay. So now, if I want to calculate that force, it's going to look like this. F equal, just like the formula we did, mu naught over 2 pi I squared, right? Because this is I1 and I2, which is I squared, because they both have the same, L, the length of each segment, divided by the separation distance between them. I'll call it D here. There we go. Okay. Now, he says in the problem, let me go back to the problem. He says, if the current I runs through the circuit, at what separation will the rod remain at rest? Which means there is an equilibrium here. Okay? Assume that the charge, okay, so they remain at rest, that means there is an equilibrium, which means this stretching, this of the spring, because of the magnetic force, is balanced by Hooke's law. Remember, F equals Kx for Hooke's law. Is that right? So here, because I have two springs, it's going to be 2Kx. Each spring will, or Kx plus Kx, that is. So that's 2Kx. See what I'm saying? So in this case, this is balanced by 2Kx. And now he's basically saying, what is the separation distance between them? Well, this x is the same as d. You see what I'm saying? So in this case, we would write it mu naught over 2 pi I squared L over x equals 2kx. Okay? So solving for x here, so how about if we cross multiply, for example? So in this case, I'm going to get 4 pi k x squared equals to mu naught I squared L, and therefore x squared is equal to mu naught I squared L over 4 pi k, and therefore x is equal to mu naught over 4 pi I squared L over k under the root. And that's it. He didn't give us any numbers, and that's basically the expression that she's looking for. Okay? All right. The last thing I want to talk about now is some problems from my notes, my lecture notes. Your book doesn't do a good job in doing those class of problems. Here's one. I have maybe 3 of them. Short one. They're all short. Imagine I have this. Imagine I have one wire like this. Here it is. And I here, I1, we're going to call it, is equal to 5 amp. Okay? And then I have a loop of wire that looks like that, right beside it. And the direction of the currents are like that. And if I assume that the distance from this wire to the left side of it is C, and the width of it here is A, and I'm going to give you those numbers, and let's assume the length of it is L, the rectangular loop here, and it has a current, we're going to call it I2, equals to 10 amp. Got it? Now, given to us that L is equal to 0.45 meter, A is 0.15 meter, and B is, C that is. Trying to erase it, there we go. 0.1 meter, okay? The question is, here's the question. Find the magnitude and direction, mag and dir, of the net force exerted on the rectangle or rectangular loop by the magnetic field of the straight current carrying wire. Okay? You can pause the video and think about it. Make sure that you understand what I'm trying to ask. Okay, let me explain it very quickly. So I have 2 wires, I1 and I2. I2 is a rectangular loop. Okay? This rectangular loop is adjacent to I1. I1 has 5 amp, I2 has 10 amp. So you got 10 amp going through it here. As you know, if you have wires with current in them, there will be a force generated there due to the current carrying wires. Okay? So now I have this side of the rectangle. See, the current is going up this way, and the straight wire is also going up. So there will be an attraction between them. You agree with me on that? However, this one is opposite, so there will be a repulsion between this side of the rectangle and the straight wire. Of course, those will not going to contribute because they are perpendicular. When the wires are perpendicular, there is no net force, and it's basically zero. So we can ignore this part right here and this part right here. Got it? So what I want to do, I want to calculate that force. Let me use a different color and just show you what that means. I'm trying to get the color. There it is. How about green? Okay, so between this, remember these are both wires in the same direction, so they will be attracting each other. So let's call this side of the wire side 1, and this one is side 2. So there will be a force F1 like that. You see what I'm saying? And of course there will be an F1 here due to the straight line. However, this side of the wire is going to be repelled by the straight wire here, and that's going to be like that. You see what I'm saying? Okay. So what I want to do, I want to find the net. You basically calculate what F1 is and what is F2, and then add them up together vectorially in a vector way. You know, this is negative, this is positive, hold it to the right, and then I add them up, and then you'll get the net. He said, find the magnitude, which basically find the number, and the direction, the net, of the force exerted on the rectangle by the magnetic field of the straight current wire. All right, so let's do it. So in this case, F1, I'm going to try to squeeze it here if you don't mind. F1, what is it equal to? Go back to the formula. F1 is right here. This is the formula. Right. I'm trying to find it. Anyway, here it is. F1 is equal to mu naught over 2 pi I1 times I2 over the distance, times L over the distance between them. Is that right? Okay. So let's find it. Now remember, F1 here, look at that. F1 is to the left, so that's going to be negative. Make sense? So here I have F1 is equal to minus mu naught is 4 pi times 10 to the negative 4 divided by 2 pi. I'll come back to it in a sec. And then I1 is 5, I2 is 10. The length given to me right here, right, is 0.45 divided by D. What's D here? D is basically the distance between the two wires, which is C for our case. See that? So this is the distance between them, basically C, and that's equal to 0.1. That's it. Plug it in. So in this case, those two cancel out. I end up with minus 2 times 10 to the negative 4 multiplied by, let me use my calculator to get that. So let's do that together. 50 times 0.45 divided by 0.1 times 2 negative 4. I'm trying to do it in one shot. And the answer is, I hope I got it right. I'm going to take this out. I'm having difficulty deleting with this pencil. Maybe I'm running out of battery or something. Come on, buddy. There we go. So we have here 0.045 Newton. I hope I did it right. Okay, now let's find F2. So this is F1. Let's find F2. So F2, basically the same formula, except now it's positive, correct? So that's going to be mu naught over 2 pi I1, I2, which is, can I just go directly? 5 times 10 times the length of the line segment, same number, 0.45, divided by how far are they from each other? Oops, sorry. How far are they from each other? It's from this wire to this wire, which is C plus A. You see what I'm saying? So that's C plus A, 0.15 plus 0.1, if you will. So this is like 0.15 plus 0.1. See what I'm saying? And we can calculate that. So F2 in this case is going to be equal to, here we have 2 times 10 to the negative 4 for the one in parentheses here, right? We've done that several times already. And then this one here, that's going to be 50 times 0.45, answer 22.5 here, divided by 0.25, right? 0.15 plus 0.1. Okay, 0.25. Now let's calculate all of that. So it's going to be 22.5 divided by 0.25 times 2 negative 4. Answer 0.18, I hope. 0.018 Newton. There we go. So therefore, the net sum of the forces is going to be negative 0.045 plus 0.018 0.045, and the net is negative 0.027 Newton. The net, there it is. That's the net force on the rectangular loop. In other words, what that means, let me give you kind of a better picture. I'll put a different color. Let's say orange. Okay. So F1 here, because of its proximity to I1, the force is greater. See, 0.045, where this one is weaker. Oops, sorry. And this one is weaker, 0.01. So in this case, if you think about it in terms of it being attracted to it, it's going to bulge more here, like that, where this one is going to be bulging, but not as much on the opposite side. Just not as much because it's much weaker. See what I'm saying? Something like that. Got it? Okay. One more. Again, these are examples from my notes. I think I'm running out of battery. I'm trying to erase the darn thing. There we go. Okay, here's another example. Okay, look at this one. I have 2 wires. There they are. I1, sorry, this one is unknown. It's a wire with current I, unknown. And this one, wire with current 10 amp. Okay? Separated by a distance D. And this point right here, I'm going to call it point A. And it is D over 2. Okay? I'm just copying things from my notes. And then I have also point C right here. Now the question is, there are 2 parts to it. Find I at point B, point A. I'm sorry, I'm reading it wrong. Find B net, I wanted to say. I have my B net at point A. And find I such that B net, which is the net magnetic field at point C, is 0. Okay? Let me explain it to you. One more thing, let me just give you one number. So here D, this one, by the way, the distance between C and the 10 amp wire is also D over 2. And then D is given to us as 10 centimeters, okay? So here's what's happening. Let me just make sure I've read it correctly. Find the B net at point A. So we want to find the net magnetic field at point A. And we want to find what is the value of I. Okay, we don't know what I is, such that the B net at C is equal to 0. Okay? What does that mean? Okay. Let's recall that from Ampere's law, we said that if I have a wire, and here is the current, and I want to find the magnetic field right here at some distance r, so that's magnetic field B is mu naught over 2 pi I over r, right? That's basically how we do it. Now, if I have two wires, well, I can just add them up together. Victoria, remember, magnetic field is a vector, so I just add them up together. So let me just forget about this problem for 1 second. Let me just give you an example just to clarify all that. I want to make sure everyone is clear on what I'm about to say. Let's say I have two wires right there. Okay, so the one, let's say this is 5 amp. This one is going up as well. Let's make it 10 amp. And I want to know the B net right here in the middle. Okay, assuming there's a distance between them, let's make it 10 centimeters, for example. Okay, I want to find the B net here. B net. Okay, if I call this wire number 1 and this is wire number 2, as far as wire number 1 is concerned, number 1, let me just go on here. B1 is equal to, again, using Ampere's law, so it's just going to be mu naught over 2 pi I over, well, how far is it from wire 1? It's 5 centimeters. Remember, this is 10 centimeters. That makes it 5 centimeters, right? So that's 5 centimeters. So that will be 0.05. And that's B1. So we could just plug it in. So we have mu naught over 2 pi. I is equal to 5 over 0.05. And then we can calculate that. Okay? Now, what about as far as wire number 2? Well, B2, again, it is right here, right? What is it equal to? And how far is it? It's 5 centimeters as well. That's going to be mu naught over 2 pi I2 over 0.05. This is I1 right here. And that's going to be mu naught over 2 pi 10 over 0.05. You got that so far? Okay. Now, using the right-hand rule, what is the direction of B1 at this point right here? If you use the right-hand rule, the direction of B1 is going to be out of the page. And if you use the right-hand rule for the 10 amp here, it's going to be into the page. If you work it out, see, if I use that, that's into the page, this one is into the page. So B2 is going to be into the page. What does that mean? Well, if you remember the sign convention, if it's out of the page, if it's positive, if it's into the page, it's negative. So that means B1 here is a positive quantity, okay? And then this one, B2, is a negative quantity based on the right-hand rule. So let me calculate all that. So I know that mu naught over 2 pi, that will be, what is it? 2 times 10 to the negative 4. Multiply this by 5. Let me just use my calculator. So that's going to be 5 divided by 0.05, and so 100. So that gives me 2 times 10 to the negative 2 Tesla, and that's positive. Got it? Okay. The next one here, and that's going to be negative 2 times 10 to the negative 4, multiplied by 10 divided by 0.05, answer is 200. So that's 200 here. And that will be negative 4 times 10 to the negative 2 Tesla. I'm reaching the edge of the screen. Anyway, there we go. And then so B net is going to be what? It's going to be B1 positive minus B2. So that will be 2 times 10 to the negative 2 minus 4 times 10 to the negative 2. And then we would calculate the net, and that will be negative 2 times 10 to the negative 2 Tesla. And that's the B net. That's basically what I mean by B net. You got that? Okay. So I want to do the same thing for this problem right here. Okay? The first part, he said, find B net at point A. Well, yes, but we don't know. I mean, B net here is due to 2 currents, I and 10, but I don't know I. So I need to do the second part first. He said, find I such that the B net at C is 0. Okay? Okay, if I look at, let me redraw that again and use the right-hand rule for it. So what I have is the following. Here are my 2 wires. Here is point C right here. Okay, and this is 10 amp right here. I hope you're taking notes. And this is I, and I is going down this way, and the 10 amp is going up like that. And we'll talk about point A later. This is D, which is D is 10 centimeters. And this one is 5 centimeters. Okay, this is point C right here. Now, first of all, I want to use the right-hand rule. What is the direction of the magnetic field at point C due to I? It's out of the page. I'm going to call this wire 1 and this is wire 2, so I can distinguish between them. It's out of the page. What's the direction of the magnetic field at point C due to current 2 or to 10 amp into the page? So therefore, B net is equal to plus B1 minus B2. Remember, into is negative. Now let's go back to the question. He says, find I such that B net at C is 0. Aha. So what that means, I'm going to equate this to 0. Okay? With this information, hopefully it will allow me to find the value of I. I is not given to me. You see what I'm saying? So okay, let me rewrite this equation again below the figure right here. So we have B net is equal to B1 minus B2 equals 0. That makes it B1 equals B2. Well, what is B1? According to the Ampere's law, mu naught over 2 pi I1 over R1, right? Equals to mu naught, I'll come back to this R1 and R2 in a sec, divided by 2 pi I2 over R2. What I mean by I1 and I2, I am calling this I1, and this one is I2. And then this one, remember, I1, I'm measuring it all the way to C, so that's R1. And then this is R2. See what I'm saying? There we go. Okay? And I know those distances because the distance between the 2 wires is 10 and this one is 5, so the whole thing is 15 for R1. You see what I'm saying? So all I need to do is you plug them in. So I have here, before I do anything, I can just do the algebra. All of that will cancel out, which is nice. I1 is I, that's the one I'm looking for. And R1 is 15, which is 0.15, equals to I2 is 10 amp divided by 0.05. And there we go. So therefore, I have just gotten the value of the current. So that's 10 over 0.05 times 0.15, and I can calculate that. So I have 10 divided by 0.05 times 0.15, and that's equal to 30. So it's 30 amp. You got that? Okay. Now the next part, which is kind of easy, really, once we get that, the next part he said, which is really the first part, he said find the net at point A. Okay, find the net at point A. How do I do that? Well, again, we can use the right-hand rule. Let me go back to the drawing. Right here. Point A is right here. As far as this point A right there, right, it's right in the middle. Okay. Now the magnetic field B1 due to I1 using the right-hand rule, what's the direction of it? It's going to be out of the page. What about the direction of the magnetic field due to current I2? It will also be out of the page. I hope you agree with me on that. So basically both are positive and they're both going to add up together. So the net field, let me put it here on the side, right there. So here B net, okay, this is all at point A. So B net is going to be B1 positive plus B2 positive. So that's going to be B net, going to be mu naught over 2 pi I1 over, well, how far is it? Remember, we are talking about those two wires here at point A. They both are equidistant from each other as far as point A is concerned. So that's going to be, it is 5 centimeters from here and 5 centimeters from here. They both have 5 centimeters. You see what I'm saying? So that's going to be I1 over 5 centimeters, which is 0.05, right? Plus mu naught over 2 pi I2 over 0.05 as well. Both positive, guys, right? Because they're both pointing outward. Now, make things simple. Take everything as a common factor. So I have, except the I1 and I2. So I have 2 pi times 0.05. And then I1 plus I2. And that gives me mu naught over 2 pi 0.05, and that will be what? I found I1 to be, in the previous problem, to be 30 amp, right there, right? And I1 is given, excuse me, I2 is given to me. I2 is 10, so I just need to put them in there. So it's going to be 30 plus 10, and that's it, basically. I just calculate that. That's giving me 2 times 10 to the negative 4. 40 over 0.05. I can do this in one shot. So that's going to be 2 negative 4 times 40 divided by 0.05. Answer, I got 0.16. I hope I didn't make any mistake. 0.16 Tesla. So that's the net magnetic field. Okay. I think that's about it. That's what I wanted to talk about. I hope this is beneficial. Please let me know if you have any questions. Bye-bye.